the kind introduction. It's really nice to be home, and it's a privilege to talk to all of you here today. Okay, so today I want to talk about data, the capabilities and the risks and liabilities of our models ultimately come from the data that we feed them. And so if we want to build safer models, more reliable models, then we have to understand what is the data we're giving them and how best can we use it. And this is not news, right? All of you probably know that recent progress in AI has been driven in large part by scaling up our training data for models and the associated compute to train on that data. So here's a graph of Meta's Llama 2 language model from last year. On the y-axis is complexity, so it's a measure of language modeling performance, lower is better. And on the x-axis is the size of the training data. And as you can see, performance just keeps improving with more and more data, even beyond the 2 trillion mark on the right side of the plot. This story about the gains from scaling up data is not just about text. It's about images. The Lion data set of image text pairs bought from the web came out a couple of years ago. Has 5 billion captions and used to train Stable Diffusion, OpenClip, and many other multimodal models. Beyond these web-focused applications, a couple of months ago, a team from University of Washington and Microsoft Research published a state-of-the-art histopathology model that got its performance by being trained on more than 1 billion image tiles from microscope slides. Just last week, you might have heard that ESM3 was released. This is a protein model. It was trained on 3 billion real and synthetic protein sequences, so on and so forth. So there's a lot of exciting work ahead of us in terms of further expanding, curating these data sets, improving how we source them, improving the quality of our data. A couple of weeks ago, we released the data LM paper. This was led by Ludwig and Weisha from University of Washington and Apple. That showed that we can get huge gains on standard benchmarks by improving how we filter our training data. And overall, there's been a bunch of recent work and excitement about open source training data sets, including data called about the DOMA, the open source training data set from AF2. So there's a lot that we can push on in this direction. We're working on a couple of projects ourselves about data selection, curation, filtering. But today I'd like to not talk about any of that work. Instead, I want to take the chance to look beyond and discuss some longer-term questions about how can we better use our data to build safer, more reliable AI systems. So, what are we going to cover? First, what are the limitations of how we currently use our data? Instead of just scaling up our training data, as we saw in the previous slides, what happens if we instead scale up the data that our models have available after training at inference time? Second, instead of scraping the data, can we generate our own training data? When and how and why might that work? And finally, what kinds of data are we missing in our current pipelines? And most of the current data that we have comes from static books, web pages, documents. So what happens when we move to more interactive settings? Okay. So that's our agenda for today. All of this work is fresh out of the oven. It's either ongoing or was put on archive in the last month. So please bear with me. Alright. Okay, so let's get started. First we'll talk about scaling up data at inference. This is work led by my students, Roland and Jacqueline, advised in large part by Seon, as well as Luke at the University of Washington. Okay. So, in the standard machine learning setting, we use our data to train a parametric model. So in other words, we are trying to take the information in our training data and then storing it somehow within the parameters of the model. And if we scale up the training data, then we have more information that we try to pack into potentially more parameters. But regardless of how large our training data is, once you've trained the model, then we don't need to keep the data around anymore. We don't use it, we just use there's a process form that's in the parameters. And so for example, this is the language model, we can then use the model directly to answer questions like this. Does immunotherapy work on solid tumors? Maybe the language model would produce an answer like that. Okay, so this is just how our standard models operate. So what are some issues with this? From a broad safety perspective, there are operations that we would like to do with our models that this paradigm does not naturally support. So for example, attribution. We often want to figure out what in the data supports a particular output, a particular statement that a model makes. For example, we might want a citation there so that we can go back and read the original article, we can verify if it's correct, we can follow up if we need to. Perhaps we want to be responsible and give credit to the data owners. And this is difficult because doing so essentially requires an inverting model generation. We need to go through billions of parameters to try to identify the one document in this massive pre-training corpus that most influence the model to generate this particular output. And people are working on ways to do this. So for example, there's been a lot of work on fast approximations and inference functions in this setting, but this is technically very challenging. What else might we want to do? Not all data is created equally. If you're answering a question like this, you might prefer to take your answer from a peer-reviewed article, from official government records, clinical trials, probably not from some discussion forums and online blog posts. And this is very difficult to do in fully parametric models, where all the training data is just chunked up, you don't know where it came from, you don't have information about the source of the data, and so it's hard to know what to trust, and this leads to sort of non-factual output, hallucinations, etc. And finally, a lot of these questions are very sort of temporal in nature. Right? So this drug is one of the most well-known immunotherapeutics. It was approved within the past decade. If you ask this question again in a few years, hopefully the answer will change for the better. If you asked this question a decade ago, you would have gotten a very different answer. And with the standard models, every time things change, every time news comes out, you have to, if you retrain the model, this is prohibitively expensive. And if you want to remove data from the model, maybe because you found that something is no longer correct, that's also very expensive. Again, there's been a bunch of work on machine learning, continual training, and so on, but those have their own technical challenges. So, what is the issue? I think fundamentally, there is a mismatch between the operations we want to do, which is on the level of data points, and how the models work, which is chuck away the data points and you just keep the parameters. And these parameters are very distributed store of the knowledge in the data. Okay. And so for example, you want to be training data attribution, you want to find a data point, but you have to invert all your parameters in order to get to it. So the natural question then is, can we build models where data points are first-class citizens? And we are going to do this via RAG or retrieval-based models. Okay. So this is not a new idea. And what happens here is, instead of only using the parameters of the model, we allow the models to have access to some sort of data store at inference time. And given a query, does immunotherapy work on solid tumors? You might go and retrieve relevant documents, for example, papers that are related to this topic. Given the retrieved documents, we can then condition on them in order to generate the model output. Okay. And this paradigm naturally supports the operations that we want to do. For example, attribution is much easier because you're attributing just to the set of retrieved documents, which is way smaller than the trillions of tokens you might have in your pre-training corpus. It makes it easier to use the source information because you can build this into your retriever. And it's much easier to update your data because you can just change what's in your data store without retraining the parametric part of the model. Okay. So what's the current state of the art in retrieval models? Prior work, especially in academia, has largely focused on some small, targeted, very highly curated data stores and on knowledge-intensive question answering tasks. So for example, a lot of work says uses Wikipedia as a data store, which is large, but not nearly as large as the pre-training corpora today. There's been a couple of work lower down from Meta and NVIDIA trying to expand data stores to larger settings, but this is generally very expensive, so it's happened mostly only in industry. Okay. And because the data store is sort of generally small and targeted, and people have only used it for a small number of tasks, as opposed to trying to build a more general purpose model. So our goal is to say, in this project, is to say, well, scaling the training data has been a very successful recipe for other models. So what happens if we try to scale the data store, to scale the data available at inference time? So what we did was to go and, mostly building our pajama data, we are building a large data store comprising a bunch of web crawl data from Common Crawl and C4, but also a lot of domain-specific data, for example, scientific papers to answer medical questions, books, code, and so on. I won't get into the technical details of how we build a data store just in the interest of time, but one of the key ideas here is, or one of the key challenges is the cost that I alluded to. How do you process and do experiments on such a large data store on an academic budget? So this is the naive pipeline of how you build a data store. And every time you want to index a data store, meaning you read through all your documents and you compute some sort of neural embedding for each of them, that is super expensive. And the problem is that every time you want to experiment with a different size of the data store, change some hyperparameters in the data store, this necessitates rebuilding and re-indexing data. So the main technical idea here is that we show that we can reorder the steps in building this data store so that we can try to push the more expensive operations first, and then every time we want to change the size or change one of the hyperparameters, we no longer need to do the expensive stuff again. We can reuse the computation and just do a much more minimal set of operations. Happy to talk about this more offline, but I'll go through some of the results. Okay, so our main finding is that when you scale up the data store, this increases performance both upstream in terms of language modeling and downstream. So here's on the language modeling side, again the y-axis is complexity, so lower is better. On the x-axis is the size of the data set. So this is sort of like the scaling plot we saw for Llama to except that instead of scaling the training data on the x-axis, we're scaling the size of the inference time data set. And we see very similar patterns, right? Monotonically increases with no obvious sign of saturation. Okay, so on the left, this is Red Pajama, this is a general web crawl data set. On the right, stock is a collection of scientific papers, so much more specialized than general web. And we see that for both cases, the larger the data store, the better. Notably, so the dotted lines are, the dashed lines are the performance of models without any retrieval. Okay, so for example, the yellow line is Llama 27B, the red line is the 13B variant. And you can see that without retrieval, of course, the larger model works better than the smaller model. But once you add data stores in, the smaller model with a large data store can do much better, at least on language modeling, than larger models without data stores. Okay. Beyond language modeling, we looked at a bunch of downstream tasks. So here are a couple of knowledge-intensive question answering tasks. which traditionally retrieval works well on. And we see a very similar story. So now the direction of the y-axis is flipped. Higher is better, this is just accuracy on the functionality benchmark. And we have a similar story of the larger your data store, the more stuff you put inside there, the better performance is. And also, smaller models with a large data store can do way better than larger models that are operating just on its parameters. We see similar results on now moving past the very knowledge-intensive QA task. We see similar results on MMLU. We don't quite get the smaller models outperforming larger models here, but we still see that performance improves pretty steadily without obvious saturation for this task. There's a caveat to that, which is that on some tasks, having a larger data store doesn't seem to work well. And this could be because perhaps the data store doesn't have the right kind of data in the right format for it, or perhaps because it's more reasoning intensive and the base model needs to be good enough in order to reason and to retrieve evidence. And this is still future work. Okay. A different perspective to this is, instead of talking about scaling the data store size, we can just talk about scaling the amount of compute you use to train. Okay? Because building a data store also requires compute. So in some sense, it's not quite fair to compare a model versus the same model with a huge data store. And we're giving more resources to the retrieval model. So on this set of graphs, we are plotting accuracy against now the total amount of compute that we take to pre-train the model plus build and index the data store. Okay, and again, so the red line here is the line with retrieval, the blue line is the line without retrieval. And we see a very similar story in that for a fixed amount of training compute that you're willing to use to build your model, it's generally much more efficient to use part of it in order to build and index the data store as opposed to trying to fit more into the parameters of the model. And this is in part because the retrievers that we use are generally much smaller than the language models, and so they're much faster to operate. Okay, so this is the overall models from AI2. We showed it on a bunch of different model families as well. I'll skip that. Okay, so takeaways from this. One is that, as we saw, so scaling the amount of inference time data through the data store in terms of the depth, like just the sheer number of tokens in the data store, as well as the breadth, like the diversity of data in the data store, can improve performance quite consistently across a range, not all, but a range of downstream tasks. And in addition to improving performance, this is an efficient use of training time compute and possibly even inference time compute. The inference time story is a bit murkier because it takes time to go and retrieve stuff, and it takes additional compute to process the retrieved documents at inference time. But if you can get away with using a much smaller model at inference time because the performance is better, then you can still have savings at compute at inference time. And perhaps more relevant to the theme of the workshop, these models make it much easier to reason about data points as first-class citizens, while at least maintaining, if not improving, the performance and efficiency of our models. And so then this enables the operations that we started motivating this project by. Can we then use such models to improve the way we attribute, improve the way we cite, to make our models more reliable because we can use more credible sources instead of just taking whatever we find on the web? Can we keep our models more up to date and so on? And there's still a lot of open challenges in each of these directions, but I think just the fact that we are now reasoning over the retrieved documents at inference time instead of having to go through the parameters to reason over a huge training time corpus makes these problems quite more tractable. Okay, so that's part one. Now let me switch gears and talk about something completely different. I want to talk about generating synthetic data as a means of better controlling and improving our training data. And this is work led by my student Scott. Okay. So, synthetic data is often used for distilling from stronger models. And so, for example, we could use GPT to generate some training data and then train a smaller model to mimic its behavior by feeding the synthetic data. Okay. This makes a lot of sense. It's very effective in many applications. I want to talk about something else today, which is, can we use the synthetic data to improve the best models that we currently have? It's not to imitate stronger models, but can we just use it as a primary source of model improvement? And this is a very tantalizing question. Right? If it works, then we will have much more control over our training data. We can make the data cleaner, safer, more targeted, and bootstrap our models. There's a recent Google paper on this topic that called the possibility of using training synthetic data, emergent self-improvement capability. This is a very safety-esque phrase, but the idea that you can just keep iteratively improving on your models. So it's very promising. And it's promising in part because just empirically, training on synthetic data seems to work well in practice. On the other hand, from an information theoretic view, there is the data processing inequality that we have to respect, and we shouldn't be able to just get something out of nothing. So what is going on here? As a sort of case study that motivated our work, there's this recent paper called Sinclair, a really cool paper from Google and MIT that just came out earlier this year. And what they did was they generated 150 million captions from number 2. They used that as prompts to generate 600 million images from Stable Diffusion. And then they trained a clip model purely on the synthetic data. Okay. And so here is the result from their paper. This is just with the real clip model from OpenAI. And on each of the columns is a different data set, supervised classification data set that they tested the model on with linear probing. Okay. And they found that Sinclair is their synthetic version. And if you just zoom in on the aircraft data set, they found huge improvements on data sets like this, where you can bring your accuracy up from 60% to 80% just by training on synthetic data instead of real data. So this is super cool. It's really, it would be cool if we could repeat the success in many other tasks. So what we sought to understand is what is driving these gains. So our hypothesis is that synthetic data is working because it allows us to control the training distribution. Right? So what does this mean? If you dig into the details of the paper, how they generated the synthetic data was that they looked at all these downstream data sets like aircraft, cars, and so on, and then they took the labels, the class labels of these data sets, and used those class labels to generate the prompts that they then used to generate the synthetic data. So the synthetic data they train on is in some sense very targeted. Right? They can control the distribution of training data to be exactly what is more relevant for the downstream tasks that they care about. As opposed to just using sort of a random selection from the internet where you probably don't have 5% of all of your images being about aircraft. Okay. So what we wanted to see is, is that the main thing that's driving the success of synthetic data, is there something else? So in particular, this is the schematic of our project. We take some real image text data set, in this case using Lion 2B. And then the method that Sinclair folk did was to use that data and train a generative model. Right? So Stable Diffusion is trained on top of Lion. You train a generative model, and then use your generative model to synthesize a whole bunch of synthetic data, and then you train the supervised model on top of that synthetic data. Okay. In contrast, you can just try to use this data directly, right, by retrieving some subset of real data from Lion 2B, and then training a model directly on top of the retrieved real data. And our goal is to try to compare these two approaches. Okay, so here's what the images look like. So each row is a type, a class. Okay, so aircraft on the top and then some ImageNet object on the bottom. The left-hand side are so way on the left, this is a real tested image that the model is being asked to classify. The left columns are the retrieved images that we take from Line-on-2B, data set. On the right are the generated synthetic images that we made with Stable Diffusion using the class labels as prompts. Okay. So just at first glance, they look like kind of reasonable. Mostly you see some airplanes, see some cats. Not sure what's going on in the fruits, but at least the airplanes and cats doing well. Okay. So how does this do? Okay. So here's the setup of the results. The first row is on zero-shot accuracy. These are clip models. So first row is zero-shot accuracy. Second row is if you do linear probing. Each of the columns is a different data set. So ImageNet on the left, aircraft, running examples in the middle. And the dashed line here is just if you use an off-the-shelf clip model, so this is the baseline performance. Okay. And we're going to plot the sort of accuracy on these data sets with the size of the either retrieved or synthetic data that we're going to use to further fine-tune our model. Okay. So one thing we can see is that we can replicate the previous results, at least on aircraft, right, which is the main data set that Sinclair showed improvements on. You can show that synthetic data kind of helps, at least in some tasks. Okay. So if you look at aircraft like this middle column, bottom row, as you increase the size of the synthetic data, you get better and better performance on this task. Okay. It doesn't quite work for some other tasks, but in general, at least on the linear probing setup, it's doing reasonably. But if you plot fine-tuning on the retrieved real images, and then we see that the retrieved images work just way better, at least on these tasks, compared to the synthetic data. Okay. And this is pretty universal across the data sets. Either they match or outperform synthetic data considerably. And so why is that? What's wrong with the synthetic data? We have some observations in our paper that I won't go through, but in this presentation, but just at a high level, there's a bunch of general distortions in the synthetic data. For example, if you squint, like this cat's face is not quite normal. Right? The engines of the propellers of this plane are like kind of distorted. So there's distortions like this. They're also class relevant distortions. So like these are class irrelevant in the sense that that cat is a bit weird, but still a cat, and like so unambiguously a cat. Whereas for aircraft, this is much more fine-grained data set where you're trying to tell different types of aircraft from each other. And this is an aircraft that's actually supposed to have just one engine per wing, but when you prompt Stable Diffusion to generate the image, it just puts another engine on it. So it actually changes the label of the class. These are the flukes that we saw sometimes, and that data is completely wrong. And maybe more subtly, there can also be differences in sort of the semantic nature of the images. Right? So for example, on the left are the retrieved images. They, for whatever reason, tend to have simpler backgrounds, right? At least in these examples. Whereas the Stable Diffusion generated ones tend to have more complex backgrounds where the cats are in different poses. Right? And this sort of distribution shift, even if the details of the cats are perfectly correct, still matter. Okay. Right. So takeaways from this is that our hypothesis, and I think the results support the fact that synthetic data is good because it allows controllability. Okay, so compared to just a uniform sample of the real data, which is basically the dashed baseline, synthetic data can improve because it allows us to shape our training distribution better. But at least in the context of image classification, if you take the real data and you try to do the same thing about controlling, like going out and retrieving specifically aircraft from line 2B instead of just taking a random sample, then retrieve data still does much better. This is also consistent with a bunch of related work, prior work on slightly different settings. So what's the takeaway of this? This definitely not to rule out synthetic data. Personally, I'm convinced that it will be an increasingly important part of our toolkit. But it means that we should, I think, be a bit more careful about thinking about why do we think synthetic data will work? Under what settings do we expect it to work versus let's just try and hope we get something for free. So a couple of vignettes on that. So just at a very high level, we have a couple of recent papers on trying to explore settings where we think synthetic data makes sense. One is when synthetic data allows us to use external models like translation models. So we have a paper taking these sort of where image text data sets, and a lot of the text might be in non-English languages. And we just run it through a translation model, convert it back to English, and show that this improves performance significantly, even on purely English Western-centric benchmarks. In addition to, of course, more representative benchmarks. Another setting where synthetic data seems to work well is when you pair it with a very powerful verifier. And so you can generate a lot of synthetic data. It might not be so, most of the data might not be great. There might be a bunch of distortions. But if you can reliably pick the best of this lot, right? If you have some sort of filter that says that you trust, and you can verify the data that you generate, then this seems to work well too. Okay. Happy to talk more about these offline. But I think that's the general takeaway, or that's where I hope we will go with synthetic data, where we are more sort of principled about identifying the conditions under which we can expect synthetic data to work. Okay, last part of this talk is on interaction data. Okay, so what other kinds of data are we missing from our current practices? As I mentioned at the start, most data in web crawls are static. Right? So you take news articles, books, patents, Wikipedia, papers, etc. And these are generally, you write them and you just disseminate them. There's not much interaction. Even the data that we crawl from user interaction on sites like Reddit, forums, and so on are not that interactive in today's pipeline, because we just take out the data, we chunk it up into relatively short chunks. You don't have the context of where the data came from, so you don't really understand the interaction patterns. So our work, this project, which is led by Stella, is to look at what happens when we move to more interactive settings. How do state-of-the-art language models work today? So standard medical, and we are looking at the context of medical question answering, because if you think about safety, right, medicine is one of the most obvious and important application areas where you really want models to be able to generate answers that don't harm their users. Okay. So standard medical question answering benchmark, this is from MedQA, which is based on the US medical licensing example. Gives you all the data upfront. Right? Like, here's the entire patient record, guarantee that it contains all the relevant info, and then they ask a question and expect you to answer it. Okay? Models do fantastically well on this. But more realistically, if you're talking about some user-facing medical applications, you don't start by saying, like, here's my entire medical record with all the relevant info. Right? You might have a patient that just comes in and says, hey, I have a fever, what should I do next? And you expect that there's some back and forth that elicits the required information. So how do state-of-the-art LMs do? We asked Dr. ChatGPT this question, and ChatGPT just gives this long blurb. It's a very generic answer. Right? It says, drink more water and get more sleep. Right? which is good advice and probably the best advice for 99% of people in this situation. But we are worried about, of course, the tail. So what we might hope that models do instead is to say, okay, well, do I have enough information to answer this question well? If not, maybe I can ask more questions like, okay, if you have a fever, how bad is it? Okay? And maybe the user will answer something, it seems like it might be quite high. The model might say, okay, actually dig into this more. Did you travel anywhere recently, perhaps? They might say, oh, where I just came from, the tropics, from Africa, and blah, blah, blah. So they could potentially try to narrow it down, and then if they decide it's more serious, then you can escalate. Okay? So this is what we aspire our models to do. So what we did in this project is to take these existing static benchmarks, and then try to convert them to more interactive settings. So the questions look like this. There's a question, there's some context, which is all the records. Then there's a question and there's some options. Okay? So in the standard setting, you get all of this up front, and you just have to answer the question. And so what we're doing instead is to hide the context. So we just give the initial info, which is like the first sentence of the record, and then we allow the system to ask more questions. It's just concretely, right, we start with this initial information, and we have a model, there's an expert system here, that determines whether there's enough information to answer. And if it doesn't, then you can ask follow-up questions, how high is the fever? And we build a separate patient model that has access to all of the patient information. And the patient model can then answer the question, oh, my fever is 2 degrees Fahrenheit, etc. Okay, and then it goes back to the expert system, which then again decides whether there's enough information to answer, and if it does, then it can give the final answer. Okay. So these are the results for the standard setting, which is non-interactive. You're given the full information up front. Okay, and you can see that we have made striking gains in the past couple of years. GPT-4 now gets like 80%, almost 80% on the bacteria task, which is higher than the average human test taker on these exams. Okay. As you might expect, if you just give it the first sentence, it doesn't do that well. It still does much better than random chance because you can kind of game these exam questions. Maybe you choose the most common answer or something, but it does much worse. Okay. And so our question was, now if you start from this limited setting, and you try to add interaction, you allow the model to ask more questions and gain more information, how much of this gap will we close? Okay. Kind of curious what you all think. Who thinks that it will close more than half of the gap? I'm asking a leading question, so. Who thinks it will close, thank you, who thinks it will close less than half of the gap? What does everyone else think? So, this is kind of surprising to us. If you just naively prompt the model, it actually just does even worse than if you don't let the model ask any questions. Okay, so there's like a negative gap that is closing. And when we dug into this, we found that it was because the language models just don't really understand the conversation format. So first, they don't normally ask a lot of questions, and when they do ask questions, they get confused by this dialogue nature, and then they tend to do even worse. Right? With our best efforts at prompt engineering to get around this, we managed to get performance up at least above the starting point, which is the bare minimum that you should hope for. But there's still a large gap in between the performance of these models and the full information setting and the best interactive setting that we could master. Okay. So still a long way to go, I think. And on these challenges, and just looking at the static settings, gives us sort of maybe a false sense of security that these systems could be safe if we then deploy them in monolithic context. And this is not just about, oh, okay, now we should go out and get more conversation data. Once we train on more conversation data, then we're set. Right? I mean, that is one part of that. But we need to adapt our methods to dealing with this as well, because once we're in the interactive setting, we start running into all the same like one policy versus off policy distribution shift issues that the RL community has been grappling with. And so here's one example that we are currently working on. It very nicely ties into Paul's work on conformal inference. So the idea behind conformal inference is that instead of predicting a single label, at least in the context of classification, instead of predicting a single label, you output a set of potential labels, if you're not sure. And the nice thing about this is that we have some sort of provable guarantees, right? At least in sort of static, IID, or changeable settings. And you can guarantee that some percentage of the time, the true label will be in your prediction set. Okay? And so we studied, now what happens if, okay, sorry. So taking one step back. So why is this relevant to the medical question answering setting? Well, if we, at any point in the conversation, we know what is the set of possible answers that the model still thinks is possible and hasn't ruled out, then we can figure out what questions to ask, right? If the set only has one element, then we know there's the answer, and we can just output the answer. If there are multiple elements still left in the set, then we can ask questions to try to disambiguate them. Okay. And the tricky thing here is that because the data is generated interactively, if we change our threshold for when are we unsure about stuff, if we change our conformal inference algorithm or parameters, then that changes the data that we get. And so if we are very unsure and we keep asking questions, then the dialogues that we get will be very long, and this might be different from the initial data that we trained the model on. So we tried to run the sort of more standard conformal, so split conformal inference algorithm on this interactive setting. So on the y-axis, on the x-axis, is the target coverage that we want our models to have. So coverage is the percentage of time that the true answer is in the output set. And the y-axis is the empirical coverage that we observe if we actually run and check what is this. And so, in the IID setting where it's static, you should get, if you implement it right, you should get something that lies on the line. But if we just try it out on the interactive setting, we find that the sort of standard algorithms seriously undercover, right? Meaning that you might think that they are supposed to be correct 80% of the time, say, but they're actually correct only 60% of the time. So this is a significant safety risk of these models, especially if you use them and then think that they are safe. Okay. So we are working on some online adaptive methods to try to bridge this gap now. And the general takeaway from this section is that many of these tasks are naturally interactive, whereas current data, current benchmarks, current methods are largely designed for the static setting. So a lot more work needed to fill this gap. I want to shout out Syrian and Brian's work from there's a paper, Uncertainty of Thoughts from NUS, that also tries to tackle this setting. Okay, now I think we are almost exactly at time. So let me end here. We've covered a few topics on how can we use our data more responsibly, more reliably, so that we can build safer models in terms of scaling up our data, inference time, generating our own training data, as well as moving to more interactive settings. These are wonderful students that did the bulk of the work, and I'll be happy to take questions.